So anyway, so having said that, so I've known Hari for quite a while now, and you know, again, like all true Buckeyes, is an amazing guy. So you know, really hardworking, you know, extremely accomplished. So he's currently a research scientist in the Department of Computer Science and Engineering. He's been holding that position since 2015. He's done it all. Okay, I mean, when it comes to high performance computing, you know, interconnection protocols, you know, parallel computer architecture, it goes on. The list is many. Okay, even for the short time he's been in academia, he's published more than 70 papers in very prestigious, you know, forums. So so he right now he works very closely with Dr. D.K. Panda on many of these problems of design and development of interconnection protocols, especially the MBA Pitch 2. I can never say it right, but this is one of their trademark tools. But today he's going to talk about some work that he has done with Anil and myself. He's at least going to talk a little bit about it, but he's probably going to talk a lot more about other things. So I'll stop now, and without any further ado, you know, invite Dr. Hari Subramoni to, you know, give his talk. Yeah. So Hari, can you start
Yep.
sharing?
Thank you for the kind words of introduction. I really appreciate that. Uh, so, hi all. So, welcome to my talk. I'd like this to be a dialogue rather than a monologue. I can keep talking about this all day. I just want to make sure that you guys are also enjoying it and liking it. So, questions are appreciated. Feel free to interrupt me if you have any at any point in time. So this talk is going to be on high performance deep learning with large scale pathology WSI images. So we've been hearing from a lot of people about digital pathology and how it has evolved. And yesterday we heard from Professor Hamid about how you apply like language models like BERT to the problems of like audio as well as textual data coming out of the nodes that the pathologists create. So I'll be briefly touching upon all of these aspects in this talk. And the goal of what we are trying to do here is, can we make things go faster? That is it in a very, very simple way. Suppose if your training of your deep learning model takes X amount of time, can we do that in a fraction of that time? It could be looking at visual data, textual data, like audio data, be it anything. Can we accelerate the process of training your deep learning models with HPC? So that is going to be the theme of this talk with a couple of case studies, for example. So let me start by doing the obvious folly of preaching to the choir. So here, let me try to give an overview of what we understand as digital pathology. So the process typically begins with the pathologist identifying histologic structures. It could be elongated follicles, necrosis, glands, etc. So the morphological appearance of these structures are an important indicator to the presence or the severity of a disease. Now, some of these structures are analyzed on a low magnification level to capture their architecture arrangements, like tram tracks and cells, or like of a papillary thyroid cancer, so on and so forth. While on the other hand, others may have to be analyzed at a very high magnification level to differentiate diagnosis like nuclear stratification or things like that. Now, due to the relatively large size of the images are tiled into patches at different resolution levels depending on the histologic structure being analyzed. And the larger tile sizes at a higher magnification level are used to preserve the cellular features as well as their architectural arrangement. So this is typically what is being done in digital pathology. So having said that, how does the modern computational pathology workflow proceed? So as we have seen in several of these talks, it always starts with the digitization of the glass slides to form large multi-resolution whole slide images. Now, each slide can contain more than like a million cells and tissue regions. So these cells and tissue regions can potentially be automatically annotated using neural networks like faster RCNN that have already been trained using, let's say, textual, audio, or visual annotations generated by human experts. Now, developing models for diagnosis or predicting clinical outcomes for a single disease can be extremely cumbersome, and it would involve a very, very, very large data set. Encompassing thousands or hundreds of thousands of slides and billions of annotated cells regions. Now, what all of this generate is a variety in terms of like it could be an audio data, textual data, visual data, or a volume of data, creating unique challenges for deep learning as well as computing. So with this volume of data, there is a very clear need to accelerate all of this process so that a pathologist can get a result in a matter of minutes instead of a matter of hours or matter of days. Okay. So in general, if you look at it, the human pathologist could create different kind of, let's say, outputs when he or she is looking at a whole slide image. It could be like visual annotations where they like maybe take a pen and circle around a piece saying that, hey, this is something we should look at. It could be a voice recording where you take up a voice recorder and say, okay, I'm looking at a slide and this is something that is interesting. This, I think this is indicative of this. Or it could be like a textual note, like a pathology report, where they say that, okay, like I observed this and this is an indicator of this. So there could be a variety of data and a large volume of this data created. Now, how do you ensure that we are able to train on such very large data sizes in time? So enter HPC. So high performance computing has been used by traditional, let's say, scientific simulation domains for the last couple of decades. So there are a lot of drivers of modern HPC architectures like multi and many core processors. So if you look at your laptop or your servers, you have very, very beefy processors in there, and you have a bunch of them. So how do you connect all of them together? So in order for one computer to talk to another computer, you need something to interconnect them. So that is where the interconnection networks come in. You also have a lot of co-processors and accelerators to help these main processors do their task. These co-processors have become so beefy and so capable that they are now beginning to replace the main processors to do the actual compute. So these are the cases like your NVIDIA GPUs, where you are doing deep learning training on these things. And finally, you have the SSDs. So we mentioned that there is a lot of data being generated. In order to efficiently access this huge volume of data, you need efficient IO devices as well. So that's where high performance IO devices come through. So all of these hardware elements drive the creation of modern high performance computing systems. And such systems have fueled the recent resurgence in machine learning and deep learning. So what really drove this resurgence? There are a few factors. So all of these techniques even existed in the early 90s. But what did not exist was the hardware capability as well as the data sets, the curated data sets, using which you could train models efficiently and quickly. So with the advent of high performance computing, techniques like deep learning, which probably training a model which probably took like a week or 2 weeks or a month, like 10 or 15 years ago, now can be done in a matter of hours or minutes. So this availability of data sets and the advent of high performance computing solutions is what has made deep learning so ubiquitous today. If you look at deep learning, it has like a couple of key phases. So one is to train the actual neural network based on curated input data sets. Once it has been trained to, for instance, say that a cat is a cat or a dog is a dog, then comes using it. So this is the inference step where we deploy the trained model to, let's say, figure out a cat is a cat or a dog is a dog. Now, if you look at the DNN training, it's a very compute and communication intensive process and can take days to weeks. This is where you need to accelerate the entire pipeline so that we can get to the results quicker. Now, faster training can be achieved by using newer and faster hardware, but there is a limit. So you need to be able to go beyond one compute element, because one compute element can only take you so far. So even with the best methods, one compute element can maybe, for instance, solve a task in like a few hours. But if you throw more compute elements in an efficient way and orchestrate the interaction between these compute elements efficiently, you could probably solve the same task in a fraction of the time. So if you look at it, this is the broad challenge and the crux of the work that we had done with Raghu and Anil. So if you look at training high-level TCV classifier using data parallelism on very large, like 1K by 1K image tiles, it can take up to 7.5 hours on a state-of-the-art multi-GPU node. So if you look at it, this is one example of training DL models based on the visually annotated data that the pathologists generate. So the broad challenge is this. It is taking 7.5 hours right now. This is completely unacceptable. So you cannot wait 7.5 hours to train a model each and every time. Can we accelerate the training of this TCV classifier using any advanced high performance computing schemes? This is the crux of the work that we had done. So, okay, now that we have identified the problem, how can we make the training faster? There are a lot of established, let's say, parallelism or parallelizing schemes in literature. The most common is data parallelism. So what does data parallelism mean? You have a problem, you chunk it up into smaller pieces, you give computer one a small chunk of it, computer two like another small chunk, computer three another small chunk. So okay, you three compute on different data sets. Finally, we can combine your results and average it out and find out where we are heading. So this is the standard way to achieve things. However, with extremely large models or extremely large images, as is common in the case of pathology, where you have WSI images which are very, very large, data parallelism kind of hits its limits, because you are not able to fit all of that into the memory of the available compute elements. So this is where newer parallelism techniques like model parallelism or hybrid parallelism comes in. Now, in this work, we kind of focus on model parallelism. So why model parallelism? So as I mentioned earlier, data parallelism, which is basically chunking up this, the entire data set into multiple smaller elements and giving it to different compute devices to do the same compute, is only applicable for models that fit in the memory of the compute element. However, if you have images which are really, really large, as in the case of digital pathology, we refer to these as out-of-core models. Data parallelism will not work. However, model parallelism, as is shown in this image, can work for out-of-core models as well, as is the case with the digital pathology. So this is a graph which shows different kind of data sets and what kind of models can be applied for those data sets on different compute architectures. So like your Pascal GPU from NVIDIA, or your Volta GPU from NVIDIA, or your Cascade Lake or Epic processors from Intel and AMD respectively. So what parallelism techniques can be applied to different data sets on different processor architectures? So that's what we are trying to show here. So as you can see, with pathology, WSI pathology images, only model parallelism will work because the data is so large that it cannot fit in the memory of like a traditional compute node. Now, in order to accelerate this, so there is a fundamental functionality issue here with respect to the kind of parallelism technique that is being used. There is also a performance issue as to how you can actually reduce the training time from like 7.5 to 8 hours to like a few minutes. So this is where the concepts of scaling up, as in using all the compute resources within a node, and scaling out, as in using multiple compute elements, come into picture. There are different frameworks available to scale up as well as scale out. What we are trying to do here is, can we use the best techniques of scale up and scale out to achieve the best training performance for data parallel and model parallel methods? So having said this, if you want to scale out to multiple compute elements, you need some sort of a parallel programming infrastructure. So there are different kind of parallel programming models available out there. The basic one is your standard shared memory model, which is what we all grew up with. You have multiple processors, all having the same view of the memory. So it's actual physical memory, which is cache coherent and all that good stuff. But the problem is this does not scale well. Then you have what is called as your distributed memory model, where the different processes know that they are sitting on different compute elements and they need to exchange messages explicitly. To let's say, here you go, I'm giving you some piece of data, I'm receiving some piece of data from you. So all of this has to be coded in the program for this to work. So this is our focus area, which is called the distributed memory model or the message passing model. So we are trying to see if we can use the message passing model to accelerate the process of deep learning training. So as Raghu very kindly mentioned, this is the key project that we work on in our lab, which is the MVAPITch2 MPI library. So this is being used by like a lot of organizations around the world, and there has been over 1 million downloads of this software stack from our site itself. For more details, please visit our website. So broadly, what we are trying to address here again is this: how can we design a model parallelism solution that is memory efficient, as in it can actually fit the very large WSI images and offer better training speeds compared to state-of-the-art systems, which is at around 7.5 hours right now. And it can also support emerging real-world use cases like digital pathology. So this work could not have been done by us alone. This was a joint work between a bunch of computer scientists, computational pathologists, and real pathologists. So we, together with Raghu and his students, as well as Anil, worked together to create this system to ensure that pathologists can reach time to solution much, much quicker. The key idea of the work is as follows. So if you look at a particular model, it has different phases. The memory requirement of each phase of your deep learning training would vary, and this is typically how it goes. But if you look at multiple phases, you would see that there are certain phases where the memory is not fully utilized. So the motivation here in our work is to see if we can intelligently design schemes and schedule computation in these phases so that all available memory and compute elements are used all the time. So our research challenges is basically as follows. So how can you have efficient GPU-based communication in deep learning frameworks like TensorFlow? How can you have efficient memory management in TensorFlow? And how can you scale these memory-aware solutions? So to achieve all of these things, we designed the model called GEMS. So GEMS is an integrated system that provides memory-efficient model parallel training and scalable hybrid parallel training. So we have proposed several schemes. I will not belabor the point in these, but through all of these schemes, the key contribution is this. We were able to reduce the training time of the TCV classifier from around 7.5 hours to 28 minutes for out-of-code training on 128 GPUs. So this is almost a 15 times reduction in training time. Okay. So this is how we achieved that. So we tried to use different kind of efficient point-to-point as well as collective communication operations in MPI to make sure that we are able to fit in the compute in a more optimal way as opposed to how it was earlier. So if you remember the earlier figure, these portions were not at all being used. So here we are able to use those portions of the compute element more efficiently to perform computation and thereby accelerate the overall execution time. So earlier, the operations would only finish by around here, but by doing efficient utilization of resources in the compute elements with additional synchronization operations, we are able to provide significant improvements in overall execution time. So we evaluated our solution on different emerging HPC systems at centers like the Lawrence Livermore National Lab. So here we were using 4 NVIDIA Volta GPUs per node, so which is kind of the state of the art. So on this, on such a system, we were able to show up to like 22x improvement in overall training time using 128 GPU. So this is a significant improvement in overall execution time for your digital pathology training workflow. So as we mentioned earlier, although our primary work was focused on how we can accelerate the visual portion of the digital pathology workflow, we have also done some follow-up work on how we can use models like BERT or other textual and voice recognition models like transformer models to see if we can apply similar schemes to accelerate voice as well as textual annotations. So currently, if you look at it, training a high-level sequence classification model using data parallelism on pathology reports like text and audio can take weeks on a state-of-the-art multi-GPU system. So can we accelerate this using a technique called subgraph parallelism? So this is something that we are trying to work on right now. So unlike the previous work on visual annotations, we have not been able to actually test this out on real pathology or real annotations and data sets created by pathologists. It is something that we are trying to do in the future. But broadly, uh, as was introduced in Professor Hamid's talk yesterday, transformers have continually pushed the state of the art in NLP or natural language processing and have achieved impressive results. So examples include BERT, as mentioned in yesterday's talk, and multi-head attention modules. So what we do here is we propose what is called super subgraph parallelism for transformers to accelerate the training of transformer models for audio and textual data. Super introduces a generalized hybrid of data and subgraph parallelism with enhanced communication patterns to achieve good scalability on modern dense GPU and CPU systems. So long story short, what is the big deal? The big deal is that using the proposed methods, we are able to accelerate the overall training by a factor of 2 when compared to the standard data parallelism approaches. So this is again like a teaser trailer to something that we want to do in the future with actual pathology data sets that we'll hopefully be working with folks in this call. So to again conclude, let me reiterate, next generation computational pathology requires the support of HPC, deep learning, and machine learning. It also requires high performance middleware designs while exploiting modern technologies. What we have presented in this talk is a set of solutions to achieve MPI driven, let's say deep learning frameworks like TensorFlow, PyTorch, and MXNet, and also propose out of 4 training and hybrid and spatial model parallelism approaches for large-scale pathology WSI images. We are looking forward to working with the pathology community. Let me conclude with a quick funding act. And more importantly, this is an acknowledgement to all the heroes that have done the hard work. So I come here and give a talk, but I couldn't have done this without the hard work of all the people listed here, past and present students, staff members, researchers, postdocs, everybody. So I'd like to give a shout out to all of these guys, without whom this work would not have been possible. So thank you. With that, I come to the end of my talk. If there are any questions, I'll be happy to answer them.
Great talk. So we still have a few minutes. So if anybody is, is willing to ask a question, that would be wonderful. Yeah.
So I had a quick question. Excellent talk, obviously, this is much needed by pathologists. Like if I look at my standard HP standard computer that I was provided by OSU to do my work in, obviously if I wanted to take my workflow to computational pathology workflow, I would need all these tools. But I think one thing which maybe make it more complicated will be even larger images and data sets, right? So we're talking about Z stacking where you have multiple levels of images, in cytology and impact that Salama just showed and others have talked about, Lee talked about it. So I think we have to be aware of those issues that make it even more complex. So, like achieving 2 to 3 times performance with a whole slide image be may not be trivial, but it'll actually be these larger data sets, which are routinely going to be seen in pathology, like cytology, will make it even more challenging. So I think you need to continue this work. That's what I'm saying.
Definitely. This is just the tip of the iceberg. So this was the initial work. Thank you, Anil. Thank you, Raghu, for your time and effort, without which this work would not have been possible. So we hope to continue working with you in the future to solve real world challenges like this. So yes, I completely agree. Yes, this is just the beginning. Definitely, we need to go forward. And yes, we hope to work with you as well as other pathologists here to see if we can accelerate solutions further.
Yeah, we live in a world driven by immediacy of access. And, I've worked with the supercomputing community for years and years. And just to get onto the CPU and to tap into the resources, there are many, many steps. And it really takes a research dedicated team to gain the kind of fluid access to HPC that you can provide. And we're there. We need that today to answer even small problems we have in our laboratory. But God, you guys are complex to work with. You have your own set of bureaucracy and tools. You have friends and family you let in because they're recognized in the HPC world, but the general researcher find it very difficult to navigate into your clusters and your expertise. So what's your solution to lower the barrier of entry of researchers wanting to work with HPC without waiting months to even gain access?
So one thing would be for us to begin speaking each other's languages. So like workshops like this, I believe would be a good place to start off. So once you establish connections, then I believe we can have like online training sessions or like work on joint proposals, work on like, let's say, joint projects, which would help us understand your. So for instance, if somebody talked to me about WSI, like maybe like 8 months ago, I would have been, okay, what the heck? So I wouldn't even know that. So now working with Raghu and Anil has, let's say, broadened my vision. So workshops like these and events like these are would be the best kind of place for you to make connections and for us to begin working with each other, so that you can help or you can guide us through what seems very complicated to us, and we can help you in a similar fashion to get onto HPC systems, get onto so there are, for instance, NSF has a lot of allocation projects which you can apply to, which is very, very straightforward, so that you can get onto an HPC system. So this happens on an yearly basis, which is called extract allocations. So we can definitely work with you on these kind of allocations to, for instance, accelerate some of your, let's say, pathology workflows or things like that. So working together, I think, would be the best for like both of us.
Yeah, having that interface, because we have Pittsburgh Supercomputing Center in Pittsburgh, and I've worked with them for over 20 years. It really takes somebody that understands their language even to fill out the allocation requests, which are quite complex. And over most researchers' heads. So how do you simplify this, or in a university create a gateway that really greases real researchers to these facilities? Because the result is, you know, and I'm sure you see it at Ohio State. I know you have it at Ohio State. There are a lot of people that just have their own clusters because you're too hard to navigate. And I have the same thing in Pittsburgh. So, and worse, we have a joint facility between Pitt and CMU investigators won't even touch the supercomputing center and set up all sorts of compute clusters. And it's just a tremendous waste of time and money and effort and personnel that could be greased if these supercomputing centers really were easier to navigate. So we got to figure out how the pathology community can engage with your exceptional resource. I still struggle with my exceptional resource in Pittsburgh. On the other hand, now I finally have a director who's the head of supercomputing center, who's done embedded research with our team before, and he's greasing the skids. But unfortunately, it's because we're friends and family that I now can gain access. I still feel and suffer for the larger community that just can't seem to navigate to your doorstep. Get into the computers and use them for all the power they are. So a lot of work to be done in this space.
I completely agree. And from our perspective, so what drives computer science research is actual scientific domains, domains that make impact on the lives of people, like, for instance, pathology. So if we can work with people, like, let's say, domain scientists, that significantly enhances and adds value to our work as well. So workshops like this and collaborations, I believe, are the way to go, because unfortunately, the two worlds speak different languages. So like, we need workshops like this to foster those collaborations, foster those connections, and let's say, enable us to speak each other's language. So for instance, if it were not for Raghu, this entire paper would not have come out, because for the life of us, we couldn't have figured out what Anil was trying to say, and vice versa. So those kind of bridge personnel, so in your case, your center director, are very key to ensure that translation between the two worlds. And workshops like this, I hope, will form the basis for that.
I think the vast majority of people doing research in this area, you know, they have maybe 2 or 3 servers with, you know, 4 to 8 GPUs each. And, you know, bringing the tools to them, you know, is where there's a lot of opportunity for impact. You know, it's great to get them on the servers, but a lot of them are, I'm sorry, on the HPC systems, but a lot of them just aren't doing that. So making it easier for them to build ad hoc clusters and to take advantage of some of this, you know, scalability, I think would really, really impact the field.